Okay, Assalamualaikum warahmatullah, and welcome to the lecture on electrochemistry. This lecture is part of the International Chemistry Olympiad 2022, and this part is basically on electrochemistry, okay, batteries and fuel cells. Okay, so before we move into electrochemistry of the batteries and fuel cells, there are few parameters which must be known before you actually go into batteries and fuel cell, because these parameters are basically fundamental parameters if you want to study before you study electrochemistry or electrical engineering, electronics, or anything to do with electron transfer. You must know these parameters. Okay, so these parameters are basically potential. So potential, what is potential? Potential is the driving force for the transport of electrons. Okay, so when we have potential zero, meaning there is no driving force for the transport of electron. Okay, so potential, the unit is a volt, but it is derived from the energy in joules per unit charge in coulomb. Okay, so potential is basically the energy required to transport a charged particle across the potential difference. So here we have it. E potential is equal to the energy divided by the charge, or it is joule per coulomb. So joule per coulomb, you get what is known as volt. Volt is a unit of potential. Okay, but potential is a relative quantity. Okay, so because when you measure potential, you must need a relative point, or the point of reference. Okay, so this point of reference does not change. So all other potential measured at different points, it is with relative to this point of reference. So meaning potential is not an absolute parameter. Okay, for example, there are many measurements which have a point of reference. Okay, meaning measurement which are actually relative. For example, if you look at the atlas, you have the latitude lines and the longitudinal line. Okay, especially the longitudinal line, because the latitude line, like for example, you divide the earth, what do you call, into northern hemisphere, southern hemisphere, so in equal parts. So the middle is the equator. Equator is 0. So meaning anything north of the equator is basically, like for example, is mentioned as degrees north, like for example 10-degree north or 40-degree north, and so on. Okay, and same thing on the other hand, there is longitudinal line. So longitudinal line, we must select a point of reference. Okay, so this point of reference is selected. It is not being calculated from an equation. It is not derived from an equation or a function. It is basically selected. Okay, so that point of reference for the longitudinal line is basically selected as a city of, a small place in a city of London. So that place is 0 degrees. So any location to the east of the city of London is basically 0 degrees east, and any location west of the city of London is basically 0 degrees west. So that is a relative measurement, meaning you must need a reference point. So same thing, like for example, batteries. Okay, like for example, you measure a battery. This is what do you call a lead acid battery. Okay, a car battery with positive electrode, or the cathode, on the left, and the negative electrode on the right. Okay, you have the blue terminal and the what do you call the red terminal. Okay, so when we measure potential, meaning the potential between the positive electrode and the negative electrode is a potential difference. Okay, or we can say it is delta, or the potential difference between the what do you call the blue terminal and the red terminal. Okay, so like for example, the potential of this car battery is 12 volts, but this is potential difference between the two terminals, or the two electrode. So we can actually mention that, okay, the potential at the anode or the negative electrode is minus 12 volt versus the cathode, or relative to the cathode, because the anode is basically the negative electrode. The one on the blue is the negative electrode. It is negative electrode. It is the anode. Okay, so it is basically negative 12 volts more negative than the cathode. So cathode is the reference point in this for A. Okay, when we choose cathode as a reference point, we can mention that the potential of the anode is minus 12 volt more negative than the cathode. Okay, so like B, like for example, if we choose to mention about the cathode, which is a positive electrode, we can say that the potential of the cathode is 12 volts more positive than the anode, because the cathode is a positive electrode. Okay, so but we don't normally mention this way. We usually say that the potential of the battery is 12 volt, meaning the potential magnitude between the negative terminal and the positive terminal is 12 volt. That is the difference, the potential difference. Okay, but by right, potential measurement is a relative quantity, because if you measure potential at one point, you must have a reference point. So therefore, that potential measurement is not absolute. It is a relative measurement. Okay, so that is potential. So potential is the driving force for the transfer of electron. Yeah. Okay. What about current? Current is basically due to the rate of the transport of charges. Okay, so that is current. Okay, so if you look at mathematical expression, I equals to dq per dt. Okay, so this current transport is, whenever you have a potential difference, then you have a current transport. Okay, because potential is driving force for the transport of the current. So current can be brought upon by the transport of electron, because one electron carries a fundamental charge, which is 1.6 times 10 power minus 19 coulomb. Minus 19, not minus 19. So that is basically the value of the charge at that electron. So one electron carries a fundamental charge, which is 1.6 times 10 power minus 19 coulomb. Is a very small value. Okay, so this is a charge, is basically a fundamental parameter. Okay, so each electron and proton in the nucleus carries a fundamental charge of 1.6 times 10 power minus 19 coulomb, except that the electron is negative charge and the proton is positive charge. They attract each other. Okay, so but this is the fundamental charge value, where each electron and proton in the nucleus of the atom carries, it has this charge value. Okay, so current is basically the transport of charges. Okay, like for example, current is basically, the rate of transport of charges. So if you write the mathematical expression, it basically is equals to dq per dt. Okay, q represents charge and t is in time in seconds. So meaning, like for example, 1 amp is basically 1 coulomb per second. 1 amp basically is 1 equals to 1 coulomb per second. But we don't write coulomb per second, but the unit we refer is actually ampere, amps. Amps equals to coulomb per second. That's the unit for the current. Okay, so the current can be due to the transport of electrons, such as electron passing from negative electrode to the positive electrode along the the wire. Okay, or the current can be also due to the transport of charges, like for example, positive ion and negative ion in the electrolyte solution. Because like for example, in the battery, you have the electrolyte. The electrolyte is between the two electrodes. So this electrolyte only consists of ions. It only consists of ion, meaning the electron cannot penetrate to the electrolyte solution. This solution is basically liquid, mostly in liquid form. You have, like for example, ions, like for example, potassium ion, sulfate ion, nitrate ion, or chloride ion, or sodium ion, Okay, so this electrolyte is basically liquid. It consists of ions. So the current transport in the electrolyte is due to the transport of ion. So meaning that electrolyte is an ionic conductor. It is not an electron conductor. Okay, and the electrode is a electron conductor. It is not an ion conductor, meaning the ion cannot penetrate to the electrode, and the electron cannot penetrate into the solution or the electrolyte solution. Okay, so so this current is basically can be positive, can be negative. Okay, by convention, the current due to oxidation is always positive, such as the reaction below. Like for example, zinc. If you look at this, I mean the Roman number 1, zinc can be oxidized to zinc 2 plus ion, and meanwhile it releases 2 electrons. And hydroxide ion can be oxidized to to release oxygen gas and water molecule, and it releases 4 electrons. This is an oxidation reaction. So the current of oxidation is always positive. Okay. On the other hand, the current of reduction is always negative. Like for example, reduction current. Like for example, the reduction of hydrogen ion. 2H plus 2 electron become hydrogen gas. This is a reduction reaction, and the current of this reaction is always negative. Or copper 2 plus ion plus 2 electron being copper metal. This is a negative current. Okay, so that is current. So current can be positive, it can be negative. Okay, whereas potential, you must, when you measure potential, the potential also can be negative, positive, but you must have a reference point. Okay, the potential can be positive or negative depending on the reference point. But current, there is no reference point. Okay, the current can be 0, it can be negative, it can be positive. Okay, so that is the description of current and also the description of potential. So when you measure current, basically there is no reference point, because the current can be 0, it can be negative, it can be positive. The current can be negative, it can be positive, as long there is a potential difference, because potential difference is a driving force for the transport of current. The current can be negative, it is a reduction reaction. The current can be positive if it is a oxidation reaction. Okay, charge and Coulomb. Going on, charge is basically the integral of current with time. Okay, because from that, from the equation, I equals to dq by dt. Therefore, when I is constant, you can say that I equals to dq by dt. That means the Q, or the current, is basically the integral of the difference of the, the current, the charge is the integral of the current with time, or the integral of delta I or delta T. So that is basically charge Coulomb. And finally, resistance. So resistance basically, how to describe resistance? Resistance is basically the opposition towards charge transfer or the flow of electron. That is how we describe resistance. Okay, so resistance is basically the how much opposition against the charge transport. Okay, so if the opposition against the charge transport is very huge, therefore the what do you call the resistance is very high. Like for example, so the resistance is derived from the two parameters which we have seen, which is the what do you call the potential and the current. Okay, which is E divided by I. So E divided by I equals to R. R is resistance. So resistance, the unit of resistance is basically volt per amps, but it is also equals to ohm. So those are the three parameters you must know before going into anything to do with electron transfer or electron transport, whether it's electrochemistry, electronics, or electrical engineering, or electrochemical engineering. These are the 4 parameters which you must know. Okay, so that is the first part. Okay, so now we move into the what do you call the second part, which is a state function. Okay, state function. Okay, state function. So I mean, this is basically thermodynamics, huh? Okay. But when you do electrochemistry, you must know certain part of thermodynamics, because the the potential value. That potential value is a thermodynamic function. Huh? Okay, the E, the potential value is basically a it is connected to a thermodynamic parameter. Okay, so what is state function? A state function is a parameter which depends on the final and initial value, not on the pathway. Okay, so meaning, because like for example, if you look at this, what do you call diagram? Okay, a state function. A state function is a parameter which depends on the final and initial value, not on the pathway between the initial and the final values. Okay, for example, enthalpy, gives free energy, internal energy, work energy. Those are basically state function. Like for example, you might heard of the what do you call the Born-Haber cycle. Okay, so the Born-Haber cycle is basically taking, it is basically calculating the enthalpy of the change. Okay, like for example, when you burn sodium, or when you react sodium metal with chlorine gas, you get sodium chloride. What is the enthalpy? That enthalpy here, this diagram here, that enthalpy here can be calculated if you know the enthalpy of the change. Because like for example, the change from the left to the right is equal to the change from the bottom left and then to on top. So this complete one cycle. Okay, so therefore here state function only depends on the initial and the final value. It does not depend on the pathway. So example of state function, like I said just now, enthalpy, gives free energy, internal energy, work, all these are basically thermodynamic parameters. Okay, whereas non-state function, okay, non-state function, it depends on the path. Okay, like for example, it depends on a path. So for example, if the initial and final values of two changes are similar, but the if the parameter which we are calculating is a non-state function, therefore the what do you call the difference between the initial and the final value, it depends on the pathway. Okay, it depends on the pathway. The best example of a non-state function is basically the electrode potential, E volt. This will come later, okay? But here we must stress that the non-state function or a path function, basically we call it a path function. A non-state function or a path function is a parameter which depends on the pathway between the initial and the final values. For example, is the electrode potential, EV. Okay, like for example, we go back to the Born-Haber cycle. Okay, like for example here, the Born-Haber cycle for the formation of sodium chloride. Look here, sodium metal plus chlorine gas, you get sodium chloride solid. Okay, so this sodium metal and chloride gas, you can actually, the enthalpy, you can actually, represent it as the enthalpy of sublimation, ionization energy for the sodium metal, and the enthalpy of dissociation from the chlorine molecule into chlorine atom, and then the electron affinity of the chlorine gas into chloride ion. You plus this together, you get the lattice energy, and finally you get the formation of sodium chloride. So therefore, the delta H for the vertical change from top to bottom, and then horizontally, and then vertically back to the sodium chloride solid, that enthalpy is equal to the enthalpy of formation. So this is what we call the Born-Haber cycle. So the Born-Haber cycle here is specially for a state function. You can actually represent the Born-Haber cycle to calculate the delta H enthalpy, or the delta G, the gives free energy, or internal energy, or work energy, because they are all state function. Okay, so this cycle only works for a state function parameter, like for example, enthalpy or gives free energy, because a state function only depends on the initial final value. It does not depend on the pathway. Whereas the what do you call path function or a non-state function, it depends on the pathway. The best example of a path function is the electrode potential. Okay, it is the electrode potential that is the what do you call the non-state function. Okay, so those are the two what do you call I mean, we have seen two parameters already. Okay, for example, I mean, we have seen 4 parameters and a state function. Okay, so going on. Okay, what is electrochemistry? Electrochemistry is basically, okay, to do with, it is subject dealing with electron transfer. Okay, whenever you have electron transfer, then you have the subject of electrochemistry coming into mind. Okay, what is electrochemistry? Electrochemistry is subject dealing with electron transfer. Electrochemical reactions are different from chemical reaction because they involve electron transfer apart from bond breaking and bond formation of chemical reaction. Like for example, a simple chemical reaction, like for example, the burning of hydrogen gas with oxygen to produce water. Hydrogen gas plus oxygen get water molecule. So this reaction only involves bond breaking, bond formation between the hydrogen molecule and the oxygen molecule. Okay, so there is no electron transfer. Basically, the hydrogen breaks into the hydrogen atom, the oxygen molecule breaks into oxygen atom, and they combine, you get water molecule. So this change is only to do with bond breaking, bond formation. So it is a chemical reaction. Okay, but how do you define or how do you describe an electrochemical reaction? The electrochemical reaction must involve electron transfer. Like for example, when you have ferrum 3 plus ion plus 1 electron, you get ferrum 2 plus. Okay, this is an electrochemical reaction because it involves electron transfer. Okay, it must involve electron transfer. So the electron from the electrode will migrate to the ferrum 3 plus ion in the electrolyte. So then you get the ferrum 2 plus. This is an electrochemical reaction. Like for example, another example, dichromate plus 14 acid plus 6 electron. That 6 electron comes from the electrode. Okay, you get chromium ion plus water molecule. This is an electrochemical reaction because it involves the transport of electron. But in these two cases, it is a reduction reaction. It is a electrochemical reduction reaction because it involves electron being consumed. Because in these two cases, ferrum 3 to ferrum 2, the dichromate 2 minus ion to chromium, it is a what we call a reduction reaction because it involves the consumption of electron. Okay, so this electron, both electron, but this electron can come from somewhere, donor, and must go somewhere because things do not come from from nothing. It must come from somewhere. It must go to somewhere. Things will not come from out of nothing. Okay, so there are two types of electrochemical reaction with respect to where the electrons are coming from and where the electrons are going to. There are two types of electrochemical reaction. The first type is homogeneous electron transfer. Okay, this homogeneous electron transfer, it occurs in the same phase, in the same solution. Like for example, when you mix ferrum 2 plus ion with dichromate ion, okay, the electron transfer is between the ferrum 2 plus and the dichromate in one solution, in the same phase, in the same solution. So this is known as homogeneous electron transfer because the electron transfer occurs between the ferrum 2 plus and the dichromate ion. Nothing else. The what do you call the meaning, like the ferrum 2 plus will be oxidized to ferrum 3 plus. It release electron, and this 6 electron will go into the dichromate. The dichromate will actually receive this electron. It becomes chromium ion, chromium 3 plus ion. So that is what is known as homogeneous electron transfer reaction. Okay, so this homogeneous electron transfer reaction, we are not interested in this discussion, in this topic. Okay, because what we are interested is the electron transfer which occurs between the electrode and the solution, which is known as heterogeneous electron transfer. Heterogeneous electron transfer must occur between the electrode and the solution. Okay, the electron can be donated from the electrode. That electrode must be an electron conductor. Okay, so you must have the electron conductor with an ionic conductor coming into contact. Like for example, in this diagram, okay, you see the electron. This electron in this blue diagram, this electron comes from the it is donated by the electrode, and you have the hydrogen ion here in the solution. So this hydrogen ion cannot penetrate to the electrode, and same thing, the electron in the electrode cannot penetrate through the solution. Okay, so therefore you must have a meeting point between the electron and the hydrogen ion. Okay, so that is what is known as heterogeneous electron transfer. Okay, why heterogeneous? Because this what do you call it, type of electron transfer, it occurs in two different phases. One phase, the first phase is the electrode phase. The second phase is the solution phase, or the electrolyte. The solution is the electrolyte. Electrolyte are solution which carries ions. Okay, so that electrolyte cannot be penetrated by the electron, and same thing, the ion cannot penetrate into the electrode. The electrode is the the electrode has electrons. It is a electronically conducting phase, whereas the solution is a ionic conducting phase. There are two different things. Okay, but you must have a meeting point. Okay, before the hydrogen ion can receive electron from the electrode, it must move towards the electrode surface. Okay, the electrons cannot move into the solution phase, and the ions cannot move into the electrode phase. Okay, so the ions will be absorbed onto the electrode surface before the electron transfer occurs. Okay, so this electron transfer occurs. This electron, for example, we are looking at this one. 2H plus plus 2 electron become hydrogen. So this type of electron transfer occurs between the electrode and the electrolyte or the solution. Okay, so the electron transfer happens in what is known as the electrode-electrolyte interface. Okay, so this is basically heterogeneous electron transfer reaction is basically to do with the interfacial electron transfer, or the electron transfer which occurs between the electrode and the electrolyte. Okay, and same thing like we have seen, oxidation is the release of electron. Okay, and oxidation always happens at the anode. Reduction is a consumption of electron, and reduction always happens in the cathode. Okay, and moving on. Okay, for example, okay, from this heterogeneous electron transfer reaction, we have two types of electrochemistry here. Two types. Okay, one involving galvanic cell, and the other is electrolysis. Okay, heterogeneous electron transfer electrochemistry involve galvanic cell, okay, in green, and electrolysis cell in yellow. Okay, if you study about thermodynamics, you know there is something which we call system and surrounding. Okay, system is what we actually put our attention, our focus into that system. The surrounding is the other part. Okay, so there can be energy transfer between the system and the surrounding. There can be mass transfer between the system and surrounding, or there cannot be any mass transport or any energy exchange between the system and the surrounding. So now, for example, so this is an electrochemical cell. Okay, the above diagram shows a spontaneous reaction in a galvanic cell. The electron will be liberated at the anode, and the electron will be received at the cathode, and there is electricity flow, electron flow, which can be used to generate work. Okay, heterogeneous electron transfer, for example, involves galvanic cell and electrolysis cell. Okay, so it is more accurate to refer heterogeneous electron transfer as electroreaction and not electrochemical reaction, because they must involve electrode as the electron donor for the reduction reaction, and electron acceptor for the oxidation reaction. The term electrochemical reaction refers to both homogeneous electron transfer apart from heterogeneous electron transfer. Homogeneous because the electron, when it's transported from the anode to the external circuit, this homogeneous. Heterogeneous occurs between the electrode and the electrolyte. That is heterogeneous. Homogeneous is to do with the transport of electron from the anode to the circuit, external circuit, back to the cathode. Whereas heterogeneous, it refers to the transport of electron between the electrodes and the electrolyte. Okay, so that is basically the the thing about this cell. So this cell, for example, okay, galvanic cell, like for example, what do you call examples are basically batteries and fuel cell, because galvanic cell is basically the electrochemistry which generates energy. Okay, meaning the electrochemical reaction at the anode and the cathode must be spontaneous. The keyword is spontaneous. That is the keyword. The keyword is spontaneous. Because if it is not spontaneous, meaning it cannot generate electron flow to the external circuit. Like for example, when we have a battery, when you put the battery, when you put the battery in your in your electronic gadgets, then you get electron transfer, meaning that battery will supply energy, electrical energy to the circuit, to the gadget. So that is basically galvanic electrochemistry. Okay, so galvanic cell can be batteries or fuel cell. Galvanic cell produce electricity from the changes in the chemical reaction at both electrode. Like for example, galvanic cell, for example, hydrogen fuel cell. Anode, you have hydrogen being oxidized to acid, become to electron, and the cathode, you have the oxygen being reduced to hydrogen ion. So these two reaction happens in a fuel cell. Okay, fuel cell. For example, hydrogen fuel cell. So this reaction are basically spontaneous, meaning it occurs without any push or without any force. It occurs spontaneously. Okay, so the key word for galvanic cell is that the electrochemical reaction at the anode and the cathode. The anode is a negative electrode, the cathode is positive electrode. Both reactions are spontaneous. Okay, so that is basically the galvanic cell. So spontaneous, we study about thermodynamics, the spontaneity, the criteria of spontaneous reaction is the delta G. Gibbs free energy must be negative. It must be negative. That is the criteria of spontaneous reaction. Okay. Okay. So continuing. What do you call? Okay. What about the electrolysis cell? The electrolysis cell is basically a non-spontaneous reaction. Okay, because this type of electrochemistry, electrolysis cell, it consumes energy, meaning you must have a power supply. Okay, when you connect, like for example, this is electrolysis cell. When you connect this power supply to the anode and the cathode, you have electrochemical reaction at the cathode and electrochemical reaction at the anode. Both reactions are non-spontaneous, meaning this reaction will not occur unless you connect a power supply to both of the electrode. Whereas the first part, okay, the anode cathode, when you connect the anode cathode, there is electron transfer, meaning it is a spontaneous reaction, like for example, battery. Okay, but for electrolysis cell, you need a power supply to bring upon changes at the cathode and the anode electrode. That is what we call electrolysis cell. Okay, so these are the two types of electrochemistry. Yeah, but for both types of electrochemistry, the reduction always happen at the cathode. Okay, and the oxidation always happen at the anode, except the galvanic electrochemistry, anode is negative. For the electrolysis cell, anode is positive. For the galvanic cell, cathode is positive, but for the electrolysis cell, cathode is negative. Okay, so this is basically the two type of electrochemistry we have in in the heterogeneous transfer reaction. Like for example, here we can summarize. Electrochemical reaction, homogeneous electron transfer, heterogeneous transfer. In the heterogeneous part, you have galvanic electrochemistry and you have electrolysis. Example of galvanic is basically fuel cell and battery, which we will discuss here. And the electrolysis part is, for example, electrolysis. Like for example, when you actually electrolyzing seawater to produce chlorine gas and sodium hydroxide. Okay, so that is basically electrolysis. Electrolysis, we always must have a external power source, power supply, because without this power supply, there can be no chemical reaction at the anode and chemical reaction at the cathode. Okay, so these are the summary of the two types of electrochemistry. Okay, so going to interfacial electron transfer. So from now onwards, we are only discussing about the heterogeneous electrochemistry. The heterogeneous electrochemistry. This is our discussion from now onwards. So interfacial electron transfer. Okay. So what is interfacial electron transfer? Interfacial electron transfer is basically the electron transfer which happens across the electrode and electrolyte. Okay. So this is our discussion from now onwards. We are not interested about the homogeneous electron transfer. Okay. So for example, if you look at this reaction, ferrum, hexacyanoferrum 3 minus plus 1 electron, you get hexacyanoferrum 2 minus. Okay, but this electrochemical reaction only involve 1 electron, but this electron is basically added into the ferrum center, because this ferrum will become this ferrum. It is basically oxidation is 3. Okay, oxidation is 3. So this is ferrum 3. 3. When you add 1 electron, it becomes ferrum 2. Ferrum 2. When you add 1 electron, it becomes ferrum 2. So meaning the oxidation state changed from ferrum 3 to ferrum 2. Meaning, but the cyanide ligands are still bonded. So this electrochemical reaction or reduction, it only involves electron transfer. Okay, this electron comes from the electrode, it moves into the ferrum 3, and the ferrum 3 becomes ferrum 2. There is no additional bond formation, no bond breaking. The cyanide ligands are still bonded with the ferrum, and no additional bond formation is taking place with the metal center or the ligands, when the reduction and oxidation occurs. The only change is the consumption of electron by the ferrum 3 and before it becomes ferrum 2. So this is basically a very simple electrochemical reaction which does not involve bond breaking, bond formation. It only involves electron transfer, meaning the electron from the electrode, it is being donated to the ferrum 3, and this ferrum 3 becomes ferrum 2. All the cyanide ligands are still bonded with the ferrum. Okay, so no change in the bonding. The only change is to do with the oxidation state of the ferrum. If it becomes ferrum 3, it becomes ferrum 2. Okay. So these reactions, so this is a very simple electrochemical reaction. Okay. How about this reaction? All these reactions are basically not simple electron transfer process because they involve bond breaking and bond formation. Like for example, 2 hydrogen ion plus 2 electron become hydrogen gas. So it must first of all it involve electron transfer. The electrode comes from the electron. It is being donated to hydrogen ion, and this hydrogen ion become hydrogen atom. And 2 hydrogen atoms must be bonded together before they become hydrogen gas. So meaning all 3 reactions involve bond breaking and bond formation. Meaning they are not only they don't only involve transport of electron, but must involve bond breaking and bond formation. Okay, so an electrochemical reaction may involve bond breaking, bond formation. It is optional. Whether bond breaking and bond formation, it is optional. But the most important thing in electrochemical reaction, it must involve electron transfer. Otherwise, it is not an electrochemical reaction. It is just a chemical reaction. Okay. Okay, so that is what we call the interfacial electron transfer. Okay, moving on. We have seen important parameters, potential and current. Potential driving force, like just for example, when you place a ball on top of the slope, it moves down. So the ball moving down is basically to do with gravity. Same thing, like for example, whenever you have a potential difference, then you will have electron flow. The electron will flow from the negative terminal to the positive terminal across the electron conductor. So that is basically the potential. Potential is a driving force for the transport of electron. Okay, so when we say potential is a driving force for the transport of electron, meaning this reaction must have a potential. This reaction and all other reaction. For example, we go back to this reaction, ferrum 3, what do you call ferrum 3, ferrum 3. When you receive one electron, it becomes ferrum 2. Okay, so this is basically a reaction which involves electron transfer. So therefore, this is an electrochemical reaction. But what is the potential difference? What is the potential? We can measure the potential of this reaction. Okay, but again, we have seen potential measurement is not absolute. It is relative. Okay, potential. We can measure the potential of the reaction, but the potential measurement is not absolute. It is relative. So before we measure the reaction, before we actually measure the potential of this reaction, we must know, we must select what do you call a reaction which is a reference point for the measurement of potential. Okay, so when measuring potential of the electrochemical reaction like the above, we must choose one reaction which is a standard or reference, has a comparison. Okay, has a comparison. So, and also we must specify the condition for the reaction, for the standard reaction, meaning the condition, like for example, pressure, temperature, and concentration for that standard reaction. Okay, so that standard reaction we choose, or it is chosen, it basically is the standard hydrogen electrode, or it is known as SHE. SHE stands for standard hydrogen electrode. Okay, standard hydrogen electrode is a half cell, and this is the reaction of the standard hydrogen electrode. The condition at this electrode half cell, basically pressure is 1 atmosphere, meaning the hydrogen gas pressure is 1 atmosphere. 1 atmosphere is basically 101,325 Pascal, okay, or Newton per meter. Okay, because before we choose the reaction has a standard reaction for potential measurement, we must specify the what do you call the condition, meaning the condition what do you call such as pressure, temperature, and concentration. Okay, those are the specified condition. Okay, like for example, the condition for this electrode or the standard hydrogen electrode is pressure is 1 atmosphere, meaning the hydrogen gas pressure is 1 atmosphere. The concentration of the hydrogen ion is 1 molar, and the temperature is 298 Kelvin. These are the condition. These are the condition. These are the condition for the standard hydrogen electrode. Pressure of the hydrogen gas is 1 atmosphere. Concentration of the ions are 1 molar, and temperature is 298 Kelvin. When these conditions are met, therefore, these are standard condition. Standard condition, and the potential of the hydrogen electrode is chosen as 0 volt. Okay, this value 0 volt is chosen. It's not being calculated from an equation or a function. It is a chosen value or a selected value 0. Okay, so this electrode, hydrogen electrode, where you have the hydrogen gas in equilibrium with the hydrogen ion concentration, I have a platinum electrode. So this what do you call this reaction, when it happens at 1 atmospheric hydrogen gas pressure, at 1 molar hydrogen ion concentration, and temperature 290 Kelvin, therefore the potential of this electrode is 0 volt. Selected as 0 volt. Okay, that is basically the hydrogen electrode at standard condition. Okay, so now we have a long list of half cell reaction, or all of these half cell reaction, meaning half cell reduction reaction, like for example, chlorine to become chloride ion, silver chloride to become silver, and so on. Oxygen become water molecule. All these are basically reduction, because reduction is a consumption of electron. or the use of electron. Okay, all of this, when all of the reaction happens at a standard condition, like for example, for the first reaction, if the chlorine gas it is at 1 atmospheric pressure, okay, and the chloride ion is in what do you call 1 molar, and the temperature is 290 Kelvin. Therefore, the potential of this reaction, this first reaction, is 1.37 volts versus the standard hydrogen electrode. Okay, so that is the value. This is how we measure potential. Okay, so all of the potential, I mean the potential of all these reaction, when it occurs at standard condition, meaning the pressure must be 1 atmosphere for reaction which involve gases. 1 atmosphere pressure, the hydrogen the ion concentration is 1 molar, whether it is a negative ion or a positive ion, it must be 1 molar ion concentration, and the temperature must be 298 Kelvin or 25 degrees Celsius. When all of this reaction has occurs at 298 Kelvin, and you have an ion concentration of 1 molar, and if we have gases, it is 1 atmospheric pressure of gases, then these are the potential value. Like for the second reaction is 0.222 versus the standard hydrogen electrode. Okay, so all of this, like for example, if this silver chloride, okay, if this chloride ion has 1 molar concentration, when this reaction happens at what we call 25 degrees Celsius or 290 Kelvin, but of course here this reaction does not involve gases, but we assume that the atmospheric pressure is 1 atm. So therefore, the potential of this reaction, second reaction, is 0.222 volt versus the standard hydrogen electrode. So that is how we get the potential of these half cells or this half reaction. Okay, so in this long list, you have very negative potential, like for example, lithium ion to lithium metal, and you have very negative potential, like for example, the case of zinc, zinc 2 plus ion where Rc2 electron becomes zinc metal. But all of these are basically reduction reaction. Okay, all of these are basically reduction, and all of these are basically must occur as standard condition. Must involve as standard condition. Okay, so those are as standard condition. So now the question is, how can we find the potential of a half cell reaction when the reaction is not in standard condition? Okay, there is a method to actually calculate the potential of the non-standard reaction by using the Nernst equation. This Nernst equation is basically the equation which allows us to calculate the potential of the half cell reaction or the full cell reaction, provided you must know what is the standard potential of the same reaction. Okay, and this is the Nernst equation. So E equals to E psi. E psi is the standard potential minus RT divided by NF ln Q. Q depends on the half cell reaction equation. So this reaction is basically this Nernst equation is basically a relative equation, because like for example here, okay, before that we go here. Okay, T is Kelvin temperature, F is Faraday constant, 96,500 coulomb per mole, and N is the number of electrons involved in the electron transfer. These are the parameter RT and NF. RT and F. T is the Kelvin temperature. What you call R is the gas constant, 8.3142 joule per mole per Kelvin. R equals to 8.3142 joule per mole per Kelvin. Okay, or joule mole minus 1, Kelvin minus 1. So that is the parameter for the gas constant. If you study about thermodynamics, you come across this constant. So those are the three parameters which are T and F in the Nernst equation. Q Q depends on the equation, how you write the equation, okay? Okay. For example, if you know the E psi or the E standard potential, if you know the, the Q, then we can calculate the E. This E, this E in the Nernst equation is the non-standard potential of the reaction. Like for example, okay. Now we calculate the Nernst equation for the half cell. Okay, take the hydrogen gas half cell. Like for example, 2H plus 2 electron become 2 hydrogen gas. Okay, the Nernst equation for this reaction, equation 1 is this one. E non-standard potential equals to E standard potential minus RT or 2F ln pressure hydrogen divided by hydrogen ion squared. Okay, so like for example, what is in this Q is basically ion concentration and gases. It does not include solid, it does not include liquid. Because this is ln Q. Ln Q here is equal to pressure hydrogen gas divided by hydrogen ion concentration. Okay, so this is the Nernst equation for this reaction. Okay, this is the Nernst equation for this reaction or the hydrogen half cell reaction. Okay, so now we see here, this Nernst equation, it gives you the relation between the non-standard potential and the standard potential of that reaction. Okay, like for example, pressure hydrogen gas and hydrogen ion concentration are the non-standard pressure of the hydrogen gas and the non-standard concentration of the hydrogen ion, meaning the pressure can be other than 1 atm, like for example 2 atm, 3 atm, or 0.5 atm. Okay, and the non-standard concentration can be other than 1 molar, like for example 1.5 molar, 10 molar, or 0.01 molar, and so on. Okay, so this is the Nernst equation to calculate the non-standard potential of that same reaction. Okay, but here the original Nernst equation is basically to do with this equation here they've given here. Okay, E equals to E naught, E equals to E psi minus RT over 2F ln. Okay, look at here. This pressure hydrogen gas black divided by pressure blue. The blue inscription, and then divided by the hydrogen ion concentration in black, power 2 divided by the hydrogen ion concentration power 2 in blue. Okay, here basically because ln, when you ln a quantity, it must be a unitless quantity, meaning that quantity does not have any unit. The unit is basically, that parameter ln or log, that parameter must not consist of any unit. Okay, so here basically, but here the unit cancel off, because here, for example, here, okay, the pressure hydrogen, the black one refers to the non-standard potential. The blue one is 1 atm. It refers to the standard potential. Same thing, like for example here, okay, the hydrogen ion, the black one, the black thing, it refers to the non-standard potential, whereas the blue hydrogen ion concentration is 1 molar. It refers to the standard potential. So therefore here, where P hydrogen H plus are standard pressure of hydrogen gas and hydrogen concentration of the hydrogen ion. So where the pressure is 1 atmosphere and the hydrogen ion concentration is 1 molar. So therefore, the E standard is a standard potential. E standard is a standard potential where it is 0 for the HCE. So here the units of pressure constant cancel each other. Okay, so this equation, this is the original Nernst equation. It can be simplified to this equation here, because of blue, because the pressure hydrogen, the blue one is basically equal to 1 atm, and the hydrogen ion concentration, the blue colored one is basically 1 molar. So it basically the unit cancel off. So this simplifies to this equation. Okay, so that is a case of the Nernst equation. Okay, like for example, because at standard condition, the pressure hydrogen equals to 1 atm, and the hydrogen ion concentration is 1 molar, so it can be simplified to equation 1. So Q remains as a unitless quantity because you have ln Q. Ln Q cannot be a unit quantity, it must be unitless. Okay, so that is the Nernst equation for the half cell. So the Nernst equation allows us to calculate the potential of the non-standard reaction, provided you must know what is the potential of the standard reaction of the same reaction. I mean the E psi, which is the standard potential of that reaction. Okay, so that is the Nernst equation. The Nernst equation can be also used to calculate the galvanic cell. Okay, so the galvanic cell is basically a full cell. Okay, this is a cell, what do you call I mean, this is a Daniel cell. Okay, where you have the copper is the positive electrode, or the what do you call, the cathode. Zinc is the negative electrode or the anode. The electron will flow from the zinc to the copper electrode, and then you have a Sol bridge. Okay, so the Nernst equation can be written for galvanic cell. Now, like for example, here we have seen, okay, zinc anode. When zinc is being with the zinc metal, it release 2 electron, become zinc ion. Okay, from the table of standard potential, I mean for the zinc, you go back to zinc. Okay, here zinc. Okay, this zinc 2 plus ion plus 2 electron becomes zinc metal. It is minus 0.76 volts. Okay, but when you reverse this, become an oxidation, then the sign become reverse. So you get so from negative you get positive. So the zinc, when you reverse it to become zinc 2 plus, and so this is the oxidation reaction. Whereas the table, you have all the reaction at the table is written has a reduction reaction. So all of them has this value. But when you reverse to it to become an oxidation reaction, then the sign will be reversed. From negative become positive. So that's why here from negative become positive. Okay, and the cathode, and this is from the table, you get the same reaction. I mean the same sign, because this is a reduction reaction. Okay, so when this reaction occurs at standard condition, it is 0.75 volt versus the standard hydrogen electrode. And when the copper reaction occurs at standard condition, then from the table, it is 0.35 versus the standard hydrogen electrode. So therefore, the Daniel cell, the overall equation of Daniel cell is zinc solid plus copper 2 plus becomes zinc 2 plus copper metal. This equation 1, when you actually when you plus this together, is 0.75 plus 0.35 volts, you get 1.10 volt. Okay, this is the potential difference between the anode and the cathode, which is 1.10 volt. Okay, this value is a difference, or a magnitude, or delta. Delta stands for the change or the difference. It comes what do you call before the E. Okay, and not I mean, because here you cannot write versus SHE, because this is a potential difference between the anode and cathode, so we don't write versus SHE anymore. Okay, as this is different between the anode and the cathode, so it's no longer related to the SHE. Okay, so to write the Nernst equation for this reaction is basically zinc 2 plus and copper 2 plus are non-standard concentration. Like for example, here we go back here, we continue, which originally zinc 2 plus and copper 2 plus ion as standard condition 1 molar. It simplifies to equation 1, which is like for example here. Okay, so this is the what do you call Nernst, the Nernst equation. The Nernst equation for the Daniel cell. It can be simplified. It can be simplified. The Nernst equation for the Daniel cell. Okay. So the Nernst equation for the Daniel cell is basically E equals to E standard minus RT over 2F ln zinc 2 plus divided by copper 2 plus ion. That is a Nernst equation for the Daniell cell. So the Nernst equation can be used to actually calculate the non-standard potential of a half cell reaction and also the non-standard potential of the full cell reaction or the galvanic cell reaction. Okay, so that is basically the Nernst equation. Okay, so for example, okay, why electrochemistry is very important? Because electrochemistry is related to energy generation, primary energy generation, like for example batteries. So like for example, this car here uses a battery which is a nickel metal hydride battery. Okay, and also you have for example quantum batteries, like for example here, and also like for example in fuel cell, hydrogen fuel cell. So these are basically hydrogen fuel cells, but there are difference between a fuel cell and a battery. Okay, so that we'll see later. There are differences between a fuel cell and a battery. What do you call so this is the time we have in this what do you call thing, and we shall continue on the other what do you call in other lecture. Okay, so I stop recording and we shall continue on the other session.